Alright, so this is Tim Elchenbronze going to explain the heuristic on my Connect 4 solver. And so in our utils page we've got Minimax, which doesn't do much on its own other than call its input as necessary in solver, where these are implemented. So we pass in populate, evaluate, and propagate. Populate is what determines whether we should stop recursing into children and their children and so on. Otherwise it'll just create children on a node. Evaluate is simply calls over to then get popped into the heuristic property of the tree. And propagate is the minimizing and the maximizing part. Over here in the board, it's using a set of 2-bit boards, one for X, one for O. We've got a cushion on the top, and that prevents wrapping around and causing a vertical connection. So that cushion helps maintain integrity while you do bitwise shifts. And then we've got this function here, shift count, which is the elemental part of score. I call it 4 times, once for every direction. So the input is direction, the other input is what player you're on. We've got a copy of the board, we shift and we end it. Once we reach connect depth, then we start actually adding the count. So we have X actual, what's actually on the board at the max, minimax depth. Then we have O's actual pieces on the board, and then we have X's potential, which is the inverse of O's board. So that is anywhere that X is and could be. So that's what will find your gaps or your future moves or anything like that. And the same thing for O, it's going to find the inverse of X's board. Of course, I'm going to clear that cushion just to make sure we maintain integrity. And then I do the same shift chaining operation. And I've got my actual weighted at 2000 and 1000, depending on which player you're at. And my O actual does the same, except swapped. Alright, so on paper, here's our board, a 4x4 board with a 1 space cushion on the top to prevent wraparound connections. A board with X isolated. And so in this case we would shift it by height to check the top left diagonal and bottom right diagonal. We shift by height, which is 4 in this case. And so every piece will wrap around and it makes the effect of shifting up and to the left. So here's our original X and our up left X. And if we AND them together, we get how many, if we count these bits by clearing the last bit and checking if it's 0, then we can count how many bits are turned on in this board, and that would be how many ordinal 2 connections we have. Here we would have a 3, that's the input to the next iteration. We're going to shift that up and to the left by shifting it by height. And we're going to AND it with the previous board. So this one here at the top and that one there at the bottom. There's 1 left, so that means there's 1 connect 3 connection, which is the same as 2 connect 2 connections. So what we would do is we would add 1 to this 3 and call it 4. The first connect 2 was picked up by the last pass, and the second one was picked up by this pass. So what we're going to do is we're going to do that again, shift it, and it, we're at 0, so the loop terminates. Only start counting after we hit our desired connect number. So for example, 4. And then that would count how many connect 4 connections we have. Alright, and then to test for things that could happen, gaps in connections, etc., what we do is we take the inverse of the opponent's board, and that's what we're going to call potential. Everywhere the X is and everywhere the X could be. And then we're going to do the same cycle with that. We're going to shift it up and to the left. We're going to add them together. You count them. You have 6. Up and to the left, and them. Count them. You have 3. Up to the left, and them. Count them. You have 1, and then you're done after that. So ignore the previous ways I used to calculate it. My final way would be putting them together. So if we were looking for connect 2's, in this case, it would be 9, 10. And so that would be 10 potential, and I can see just by looking at here, and 2 actual. You got 1 there, and another 1 there. This is heuristic vision, or Minimax vision. It's basically its selected board. This is the best board. These are my values on all the different columns at root level. So we can see we valued middle at 74, and we're going for a maximize here. You can see it all taper off like it should. And yeah, I just exposed a little flaw there. Looking far enough ahead that it says, oh, I can win by here before X wins here, but there's problem detecting order that is within its search depth. So there's my flaw as I explained here, so I can go ahead and go 6 and win. We're going to cancel you, and we're going to run it again. When it's playing against itself, it does a lot better, because it knows exactly what the other player is going to do. Whereas when you're playing with a real player, well, not so much, and that's where it needs that extra feature.